To the lecture. So we're talking about camera calibration, and remember that what we discussed was that you have something that's called a calibration grid that gives you a number of 3D world points and 2D image points. This is a toy example of what this looks like. In reality, they are huge, right? But they're too large to bring here in class. But this is like a very toy example of this, right? So you see that there are these parallel lines, horizontal and vertical lines, and at each intersection that defines a three-dimensional world point. My origin 0, 0 can be right here, the intersection of the three axes, the three basis vectors that define that three-dimensional Euclidean space, right? And therefore, every point in the intersection of these lines, it's given to me. So I can put this right here, and that's my world coordinate system right here. Okay? And that's given. And then with that, I can obtain my camera points. So I have, let's go back to, let's rewrite this. With that, I have my three-dimensional point Pi. And remember, I have my matrix M that defines the projection from the 3D world to the 2D image. And I'm going to take the first row of M. So M, capital M is M1 transpose, M2 transpose, M3 transpose, the three rows of that matrix. And if I divide this by P3, right? This is equal to my first value, UI, in the image, and VI is M2, PI, M3, PI, right? That's our perspective projection camera. And then what we are going to do, we're going to solve this system of equations using linear least squares, right? So we introduce linear least squares. And in general, linear least squares, remember, if I have q variables, so x1 through xq, and I have p equations, so x1 through xq equals 0, and then I have my corresponding coefficients here, my u's, u11 through u1q, are the coefficients of the first equation, u21 to 2q, the coefficients of the second equation, and so on up to p, right? And I can write this in matrix form. So I can have ux equals 0, where x, it's a vector of x1, x2, xq, and u is the matrix of coefficients, and that equals a vector of zeros. And then linear least squares, remember, minimizes the least squares error, which is nothing else than ux square. I want to minimize this, right? And what's ux square? This is x transpose, u transpose x, right? Oops. U ux. Okay. Now this is a q by q matrix. It's also a symmetric matrix, right? And it's positive defined. Now, we already saw what happens when this equation right here equals, instead of 0, equals y1 through yp, right? then in that case, this is equal to my vector y. And then from here, we derive the linear least square solution. So the least square solution is the pseudo-inverse of U, which is U transpose U inverse U transpose, right? So that's my solution. So I can write, if you will, you can write X is equal to the pseudo-inverse, right, times Y. Okay, excellent. But what happens when I have homogeneous coordinates, meaning that now my y's are equal to 0? Then in that case, I have ux equals 0. And that means I want to minimize ux squared, which is equal to this quantity here. And that gives me this matrix right here, which is a square matrix, right? U is not, but this one, U transpose U, is a square. It's symmetric, right? Because I'm multiplying every row of that matrix by itself, and therefore that's a symmetric result. And it's positive defined, because if I multiply every row by every row, every column by every column, right, then that's like every column squared, and that has to be positive by definition. So it's also a positive matrix. Now, for those of you that know what this means, that means that this defines a specific type of distribution called a Gaussian. If you don't know that, don't worry about it. All you have to know is that you can compute, let's call this matrix A. You can compute the eigenvectors of A and corresponding eigenvalues. Let's call them V and eigenvalues. Let's call them capital lambda. Okay? So we're going to have V is a matrix whose columns are the eigenvectors. So I'm going to have V1, V2, up to V, what did we say? How many? P or Q? I forget. Q, right? Yeah, Q, right. Q. And capital lambda, it's a diagonal matrix of corresponding eigenvalues, lambda 1, lambda q. And you can either assume that lambda 1 is larger equal than lambda 2, larger equal than all the way lambda q, larger equal than 0. Or you could assume lambda q, it's the largest one, and lambda 1 is the smallest one. It doesn't matter. Okay? Just pick one. So let's see how we can use this method, linear least squares, to solve a problem which is related to the problem that we're interested in, which is this one here for camera calibration. Okay? So imagine that I'm in the real space of 2 dimensions, and I have a number of vectors in that space. So let's say that I have vectors like this. And I want to find the line that best approximates all the vectors that I have. Okay? I have the best fit for a line to a set of points. So I want to fit a line to a set of points of vectors xi. Okay? Actually, let me call them pi instead. Pi, and since I'm in 2D, this is xi, yi. That's what I'm going to do. Okay? Now, how am I going to do that? Well, let's start with the first definition. I'm going to define the equation of a line. The equation of a line is ax plus by equals some d, right? Some offset. What this represents is a and b here, is a and b represent the normal of my line, right? So this is AB represent the normal of that line, okay? And D represents the offset, right? The distance from that line to the origin right here. So D is the offset. Now, what do I want to do? My goal is to find the best fit of this line to the set of points that I have here, right? These PIs that I have. So in other words, let's write this goal mathematically. I want AXI plus BYI minus D to be as small as possible for all I, right? So I want to find a line such that when I substitute the value of xi, yi for every point, right, this result is as close to D as possible, which is same as saying this equal to 0, right? I want this to be as close to 0 as I can, right? Okay. Now, I want to do this for every possible point that I have I, right? So 1 through P, is that what we said that we have? Or N, okay. And the number of points that I have. So I have P1 through Pn, these are my points. And I'm going to call this some error function E. And my goal is to minimize E, okay? Now we know one more thing. We know that the norm of our normal vector has to be equal to 1, right? The 2 norm has to be equal to 1. That's the normal vector, has to have norm 1. That, simply put, means that n, which is equal to, n is equal to ab, and therefore a squared plus b squared has to be equal to 1. That's our constraint. Now, since we want to minimize this, I'm going to take the derivative of this function with respect to the third variable d. So I have 3 variables, a, b, and d. So I'm going to take the partial derivative with respect to d, and I'm going to equal this to 0, right? And the hope is that I'm going to find the inflection point, right, at which that value e is the minimum, right? Because at the minimum, the derivative has to be 0, right? Okay. So let's do this. So this is going to be equal to, let's see, oops, I forgot my mistake. I forgot here a square, remember, that we had from last time. Therefore, list squares. That's the squares part. Okay, so I have 2 times thus the sum over all I of I'm deriving with respect to d, so the derivative of this with respect to d is equal to -1. So I'm going to add the negative here and times this component, which is axi plus byi minus d. And all this has to be equal to 0. So let's see. This sum of xi's and sum of yi's, I'm just going to call them x bar and y bar, which are nothing else than 1 over n, the sum for all I of the corresponding xi's and yi's. And therefore, I can write that, what am I going to do? Oh, here. I can write that ax bar, right, from here. So I'm putting this inside. So, and this is going to be equal to this. Ax bar plus by bar is equal, or minus d equals 0. I'm just going to move d, I'm going to move d to the other side. So equals d. Okay, good. I'm getting somewhere. So now I can rewrite my equation here, right, using this result. I can rewrite this equation as the sum from 1 through n of a xi minus x bar plus b yi minus y bar square. And all I did here is substitute this d here by this value, right? And I obtained this, correct? And that means that my u that I had, remember, the matrix u of the coefficients that I have here is going to be equal to, well, these are my coefficients. So the first one is x1 minus x bar, right? The second one here is going to be y1 minus y bar, and so on up to n, I said, right? xn minus x bar, yn minus y bar, right? That's my u, correct? And remember that we have a constraint that, what is it? Right here, that the norm of the vector is 1, and therefore this has to hold. Therefore, I can do minimize u and square, right? Which is again equal to n transpose u transpose un. And then n has to have a norm 1. So if I compute n as the eigenvectors of u transpose u, right? Those eigenvectors also have norm 1. So they actually are equivalent to my unknowns here. And since this is going to be, so if I substitute this for an eigenvector, let's say I substitute this for my eigenvector vi, right? Remember, where do I have this here? I substitute this for one of my eigenvectors, right? Then this equation is going to be equal to, anyone? Is that? Yep, lambda I. Very good. Right? So because I want to minimize, right? My goal is to minimize this. Which of these lambda do I prefer? lambda q, right? So I'm going to have n equals vq, right? That's my solution for n. I'm almost done. N equal to vq is going to give me a and b. And once I have a and b, I can substitute them here and obtain d, right? So with these two equations, I can get a, b, and d, right? And that's how I find the best fit of a line to a set of points in 2D-dimensional space. Okay, any questions? Clear? So we'll do a homework. We'll do the same thing as I've done here now today, but we're going to use linear least squares to fit a plane to three-dimensional vectors. So now my PIs are going to be equal to xi, yi, zi, right, in the real domain of 3 dimensions. Okay. You need to solve this, right? Redo all the equations that we have done here, but for 3 dimensions instead of 2, and B, provide the MATLAB implementation, right? That given a number of points, it finds that plane and it draws the plane in 3D, visualizes the result. All right, any questions? Nope. So let's go back to now our problem, our original problem, camera calibration. And now we're going to redo what we did here, but apply it to these equations that I have, right, for camera calibration. Okay, let's do this. If you want to work in image processing, computer vision, machine learning, speech analysis, networking, I don't know, a variety of other things, at least 30%, if not 50% of what you can do can be done with linear least squares. That's how important this is, okay? So we're really going to spend a lot of time working with linear least squares. For those of you that are taking my machine learning class right now, they will know that one of the first things that we cover in the course, which was the covariance matrix and the correlations, was computed using linear least squares, right? Rather than computing, I should say derived. Okay. So again, I have a calibration grid like this. I place it somewhere in my world. I put my cameras. I take pictures of this. And now I have this equation that I erased. So let me write them again. So I have my matrix, my projection matrix M. M is the projection matrix that determines how I take pictures. And my perspective projection equations are M1 transpose minus UI M3 transpose PI equals 0, and M2 transpose minus VI M3 transpose pi equals 0. If this look different than the ones I had before, they should not, right? Because the ones I had before is m1 pi transpose over, actually m1 m3 transpose pi, right? And all I've done, and this is equal to ui, I've moved this to this other side, m3, so this is ui m3 pi, right? And this one then negative to the other side, which is m1 pi, right? The same equation. So these are the same equations I had before. Now let's write them in matrix form, as we like to do. So I'm going to have two matrices, the U matrix of the coefficients. Where are the coefficients here? The pi's and the ui's and vi's, right? These are my known variables, right? The coefficients. Okay. So I'm going to write pi transpose, 0 transpose, meaning rows. This is a row of zeros, not just a 0. Negative ui pi transpose. And 0 pi transpose, negative vi pi transpose. So this is my matrix mu. Now this multiplied by my matrix of unknowns. What are my unknowns here? My unknowns are m3, okay. M1, M2, and M3 are my unknowns. So I'm going to write them here as M1, M2, and M3. Now be careful what I did here. Now before, when I had that other, those other equations written down on the whiteboard, they were the x vector, right, of unknowns, x1 through xq. Remember that? That is a vector too. That means that I take the first row of M and I transpose it to be given as a column, right? So this is the first elements of M1, so the first row, then the second row, and the third row. But since they are transposed and they are columns now, then this is a vector of unknowns, okay? And this is equal to 0, 0. Okay, now note that this is for each observation that I have, for each three-dimensional point, capital Pi, and corresponding image points, ui, vi, I get this system of equation, right? But in general, I have n three-dimensional points and corresponding two-dimensional image points. So let me write this for all the equations that I have, all the knowns that I have. Oops, they should be U1, Pi, so P1 transpose, 0 P1 transpose, negative V1 P1 transpose. And then I'm going to repeat these terms, right, these three terms for all the n points, three-dimensional points that I have, and corresponding two-dimensional points. So negative un Pn transpose, 0 Pn transpose, negative Vn Pn transpose, right? And let me call this capital P. And now what do I want to do? My goal is to minimize the error function, this capital P times this m vector here, m vector squared, right? That's my goal. I know how to do that. All I need to do is do an eigenvalue decomposition of P transpose P, right? So I need to do an eigenvalue decomposition of this. That's the same as P transpose P. It's times v, it's equal to v capital lambda. V, the same that we defined before, the eigenvectors v1 through v12 in that case, right? Because this is a matrix M, right? Right here that has M columns. So this is an M vector of 4 elements, 4 and 4. So this is 4, 8, 12, right? So I have 12 eigenvectors because obviously this is 12 by 12. And corresponding eigenvalues, the diagonal matrix of lambda 1 through lambda 12. And my solution, M, my vector M, is going to be equal to V12 because that's the one that has the smallest error, the smallest least square error, and therefore that defines my solution for M. Now I take the first 4 elements of that vector and I write them here as a row, the next 4 elements as the second row, and the last 4 elements as the third row. And I have my projection matrix. So let's review what just happened. I built a calibration grid. I placed it here somewhere. Okay. I took a camera. I have no idea what the projection matrix M of that camera is. I'd have to know the focal length. I'd have to know the aspect ratio. I'd have to know all the parameters of the camera, right? The intrinsic and extrinsic parameters. I have to know the distance from the pinhole to that calibration grid, the rotation matrix between these two coordinate systems, everything that we have defined, intrinsic and extrinsic parameters. I have no idea what that is, right? But here I take a few pictures. I take just one picture of this, and then for every 3-dimensional point here, right, the intersection of these lines, I know the 3-dimensional coordinates. I also know the 2-dimensional ui's and vi's corresponding to these capital P's from my image. And I write them here, right? These are my P1s, U1, V1, all the way to all the points that I am using. And then I compute, if that matrix is called P, I compute P transpose P. I do an eigenvalue decomposition equation. In MATLAB, for example, this is called Eik, the function, Eik of P transpose P. And then I take the eigenvector associated to the smallest eigenvalue, right? And I equal M to this. And then I reconstruct my projection matrix that I have no idea what it looks like by taking the first 4 elements of that vector and writing them down as the first row, the next 4 elements as the second row, the last 4 elements as the third row. And all of a sudden, I have the projection matrix of my camera that specifies all the intrinsic and extrinsic parameters of that camera in the world coordinate system that's defined by these 3 axes and origin that I have here, right? Isn't that cool? This is stunning. I have no idea what my camera is or does, and yet I can easily compute the projection matrix. This is unbelievable. Now, you have seen for sure at some point applications that start especially in television where they'll show, for example, in football, that was very common, still common, where they will draw 3-dimensional graphics on the field, right? And if you've played that game, that phone game, Pokemon Go, is that the name, right? It will draw 3-dimensional characters wherever you point the camera, right? And nowadays you have applications from furniture stores where you point to a room in your house and it will place a bed or a chair or a table, whatever you want to buy, and you can see how it's going to look, right? How on earth can they do this? It's actually really easy. If you have the 3-dimensional coordinates of that object, and you know your projection matrix, you can solve it very easily. Now, in the phone application, it's a little trickier, and that's something we cover in computer vision, how to do this, because you have to know where the line at infinity is from the image that you take and solve a couple of equations. Actually, really easy computations, but it takes a little bit more math to do so. But for the application in football or any other thing that you do on television, the way they actually do it is by using a calibration grid. It doesn't look exactly like this, but the day before the game or hours before the game, they actually go down on the field and they place certain markers, and then they take images of this, they compute the projection matrix M, and they have all the cameras calibrated, and then they can project any three-dimensional graphics on the two-dimensional screen. Right? That's simple. It's just applying the projection matrix on your three-dimensional object. You obtain the coordinates of the image. It's pretty cool. All right. Now, if you want to be even more precise with your projection matrix, what you can do once you have your matrix M, you can now recover all the intrinsic and extrinsic parameters that we have defined in the perspective projection camera, right? Let's see how we can do that. Let's do step by step. See how we can recover every single parameter of that camera. And that's really cool because it then allows you to change one parameter at a time, and it allows you to see things from different cameras, even virtual cameras that do not exist or you don't have. Okay. So remember that our projection matrix M is nothing else than a matrix A, that's a transformation, right? And a vector B, which is a translation, right? And in our case, we show that this is equal to K, the matrix of intrinsic parameters, times the extrinsic parameters that include a rotation and a translation from the world coordinate system to the camera coordinate system, right? Okay. Now, this, of course, it's defined up to a scale. So in reality, there is a scalar here. Let's call it rho, right? Because all these equations are in homogeneous coordinates, so this is defined up to a scale. Now, as we've done before, let me call the rows of A, A1 transpose, A2 transpose, and A3 transpose. And therefore, I'm going to write this times rho, my unknown, is equal to, this is the matrix that we derived in our last lecture. Alpha R1 transpose, alpha the cotangent of the angle of the physical retina, remember? R2 transpose plus U0 R3 transpose. And I had beta over the sine of the angle, R2 transpose plus V0 R3 transpose, and then R3 transpose. Now we have also assumed, right? Remember, we have made an assumption when we have solved for this M. Actually, let me not write this here. I don't want to confuse you. When we have done this, we've assumed that that M has a specific norm, which is 1, and that's because the norm of an eigenvector is always 1, right? So we have made that assumption. That's what defines our scale, our particular scalar, right? That we have defined. Now, if you need a refresher, a matrix norm is a function. This just, let me do this here. A matrix norm is nothing else than a function from m by n dimensions, right? So a matrix of m by m dimensions onto a number, a real number. And it has to have the following properties. F of m, of our matrix M, has to always be larger or equal than 0, right? F of M1 plus M2, where M1 and M2 are two different matrices, has to be smaller or equal than F of M1 plus F of M2. And F of alpha M has to be equal to alpha Fm, right? Any metric or norm, excuse me, has to abide by these properties. For matrices, the most common norm that we will work with is called the Frobenius norm. Which I'm going to specify with a capital F here. And the Frobenius norm is given by the sum of 1 through m and 1 through n for all the rows and all the columns in my matrix of every entry, right? Mij, it's the entry of the ith row, jth column of my matrix squared, and then square root, right? That's a Frobenius norm. Now, this may look familiar. If those were vectors, that would be the Euclidean norm or the 2 norm, right? But in matrices, it doesn't work like this. Actually, the 2 norm of a matrix is something else. It's actually related to the eigenvectors, okay? We'll probably see this later in the course. Okay, so let's go back here. That's where we are at. Let's start with the rows of our rotation matrix. Our rotation matrix is R1 transpose, 2 transpose, 3 transpose, right? And we know that since this is a rotation matrix, these rows are orthogonal to one another, right? So the inner product of Ri transpose Rj, right, has to be equal to 0 for I different than j, and 1 for I equal to j. So I know that Ri transpose Rj is 0 for every I different than j, obviously. If they are equal, then Ri transpose Rj for I equal to j, then I just have Ri times Ri. This is the 2 norm of a vector square, which in that case, because it's a rotation matrix, this is going to be equal to 1, right? All right. So let's get the equations out of this. So I'm going to start with the first one. Rho equals some epsilon divided by A3. Epsilon is going to be positive or negative. And that is given simply by this equation here, right? So rho equals this or this. Okay, same thing. R3 is equal to rho A3, right? R3 equal rho A3. U0 which is here, you can factor it out as rho square A1 inner product with A3 and V0 rho 2 A2 A3. Whoops. And what else? I'm going to use the fact we know that our angle, the physical retina of the two axes of the physical retina, it's approximately 90 degrees, right? So with that, I'm going to compute A1 cross product A3. And A1 cross product A3 is going to be equal, if you do it here, you are going to obtain, you can do that at home, negative alpha R2 minus negative the cotangent of the angle R1. And if you do A2 cross product A3 again, then you're going to obtain this portion right here. You can do this at home again. Beta over the sine of the angle times R1. And if I do the norm of A1 cross product A3, this is going to be equal to alpha, the absolute value of alpha, the sine of my angle in the physical retina. And if I do this for A2, A3, this is going to be beta divided by the sine of the angle. Now remember that we gave these properties for the skewness and the aspect ratio of the camera. Remember that? And now that I have all these equations, I can solve the system of equations that I have here. And if you do that, you have to obtain R1. I'm going to take R1 from here and here. So R1 is going to be equal to rho square the sine of the angle divided by beta times A2 cross product A3, which is also equal to 1 over the norm of A2 cross product A3 times A2 cross product A3. Okay. Oops. Better. And R2, which I cannot compute, but look at this. R3, it's already given, right? We have it here. Where is it? I already know R3, right? R3, it's plus minus A3. And A3, it's, of course, known to me. So if I have A3 and I have R1, and I know that all of those are orthogonal to one another, then R2 is given by R1 cross product R3, right? Okay, so I have R3 here, I have R1 here, and I have R2 here. All right, I've recovered the rotation matrix R. Great. Now I need to recover the angle and the alphas and betas, remember, which are the aspect ratio times the focal length of the camera. So let's do that. The cosine of the angle was nothing else, if you remember. Again, this is what we did in the last lecture, was A1 cross product A3 dot product with A2, A3 divided by their norms, A1, A3, A2, A3. And alpha, it's going to be equal to rho square A1 cross product A3 times the sine of the angle and beta, it's again rho square A2 cross product A3 times the sine of the angle. All right, excellent. So now I know the rotation matrix here, and for K, I know my skewness of the camera and my focal length and aspect ratio. Cool. All right, we have everything that we need. Are we missing something? So we have all the intrinsic parameters. We have R. We miss something else? Maybe the translation would be useful, right? Okay, so all I have left is the translation. So let's get the translation, and I'll be done. Practice this at home. It's important that you know how to use linear least squares and then obviously solve a system of equations like this, because this is pretty much what you'll be doing in any area, not only image processing, any area where you apply linear least squares, you're going to have to solve this system of equations, right? So let's see, I have K R T, it's equal to rho AB, right? So K times T is equal to rho times B, which means that T is equal to rho K inverse B. Oh, there we go. Not that hard. So you can also recover the translation, right? Awesome. So now I have all the intrinsic parameters and all the extrinsic parameters of the camera. Now, when you do this in your project, right, when I'll give you some images of a real calibration grid, not just this, right, but a real one. And what you're going to do is, you know the three-dimensional coordinates of that calibration grid. I don't have to give it to you. I mean, it's a calibration grid. Right? The distance between every line, you can assign it to whatever number you want. It's a scalar, right? So let's say 1. The 0, 0, 0 coordinate, the origin of the coordinate system, you know what it is. It's right there at the center point of where the three axes cross. And you need the image coordinates, right? And there is a function in MATLAB, G-input, that allows you to click with the mouse at each point, and that returns a U, I, and VI of that pixel. Okay? So you can construct all these matrices that we have shown here, do an eigenvalue decomposition, obtain the matrix M. From M, you can obtain A and B, and from A and B, you can obtain R, right? This, and this. Then you can obtain the skewness of the camera, the focal length and aspect ratio of the camera, and the translation. And then if you want, you can play with this, right? First, you have already recovered M and K, R, and T, and therefore you can plot things on top of the image. So one easy thing to check whether you have recovered the correct M is to redraw the calibration grid on the image, right? So you construct the calibration grid in 3D, right? 0, 0, 0 for the origin, and then this point here, if this is the x-axis, let's say, right? This one here, there will be 1, 0, 0, and this one, 1, 1, 0, right here, right? And this one here be 1, 0, 1, and so on, right? So you write this in 3D, and then you project it with M onto the image, and then you can redraw it, right, on top of the image. and you'll see that it should align perfectly, right? You can also reproject the lines if you want. Just really cool too, right? The equation of a line, and you just reproject the line from 3D to 2D. And you can actually start drawing things on that image. The next thing that you can do is you can play with the parameters of the camera, right? So you can start changing the parameters of the camera and see what happens, right? If I change the parameter for the camera, I redraw the image, what am I going to see? And that will tell you what parameters do for this specific camera that you have used or that I used to take that image, right? I don't even remember what camera I used maybe 5-6 years ago when I took these pictures of the calibration grid that I used in this project, right? But I have an algorithm to recover my calibration matrix, so, or the projection matrix rather, so it doesn't matter, right? I can know this pretty quickly. All right, when you do that, you have to be very careful how you select the points on the calibration grid, right? So I'm going to give you an image of the calibration grid, and you have to be careful. You cannot just select any point or any set of points on that calibration grid. It has to span the whole space, meaning the 3 planes. Let me show you what happens if you don't do that, because this is actually very interesting. It's called a degenerated solution. Okay, let's see. All right, so what am I going to do? Remember, I have P times my matrix. Let's call my solution for M, right? I'm looking for the solution vector M, right? M is what I want to find. Let me call it L. That's my solution, equals 0. And L here is L1, L2, L3, the 3 rows of M, and each Li is given by 4 elements, remember? So Li1, Li2, Li3, Li4, correct? Now, PL is equal to my P1 transpose 0, negative U1 P1 transpose, 0 transpose P1 transpose negative V1 P1 transpose, right? All the way to the nth point. And 0 Pn transpose negative Vn Pn transpose, right? This is the P matrix that we had defined times L, which is this vector here, which is L1, L2, L3. And now let's see what happens. If I do this matrix multiplication, I'm going to have this first row times this vector, right? So I'm going to have P1, right? This one here, multiplied by L1. 0 plus, I would say, plus 0 times L2, 0. So I'm not even going to write it. Minus U1 P1 transpose times L3. So far, so good? Yeah? Okay. Let's do the other one. 0 times L1 is 0. P1 transpose L2, right? Minus V1 P1 transpose times L3. Yep. And I do that for all the endpoints. So I'm going to have Pn transpose L1 L1 minus UN Pn transpose L3 and Pn L2 minus Vn Pn, this is V, Pn L3. Okay, excellent. Now remember where this came from, right? This came from the equations that we started with, which are U1 and V1 equals to M1 P1 M3 P, or let's call it I, VI M2 PI M3 PI, right? That's where what we started with. So now let me combine this with this, so make the equality. And from these two equations, I can write, let's see, I'm going to have UI VI here, right? So I'm going to have these equations here. So I'm going to start with this one. How about this one? I'm going to start with PI transpose L1 right here minus UI, right? This U1 here, UI, which is equal to this thing, right? Okay, so let me write this down. M1 transpose PI and M3 transpose PI. Excellent. And what else do I have? PI L3. Okay. And that has to be equal to 0, right? I mean, this is equal to 0. And now let's go to the second row. For the generic case, it's going to be PI transpose L2, right? This is a 2. Minus VI. What's VI? VI, it's M2, whoops. It's M2 transpose PI, M3 transpose PI, right? This is VI. So, and now PI L3 equals 0. Great? Yep. All right. Let's try to simplify this a little. I can take this PI out. So I'm going to have PI transpose. I'm pulling it out. L1 M3 transpose minus M1 L3 transpose PI, it's equal to 0. Excellent. And from this second equation, PI transpose L2 M3 minus M2 L3 PI also equals 0, right? Same equations, just rearranging the terms. Okay. So from here, if I can find my marker, it would be nice. Oh, there it is. So from here, we want to find a solution. Now, let's see how we can find a solution. So this has to be equal to 0, right? Which means that PI is not 0. So this equation here, right, in the parentheses has to equal 0, right? Okay. So I have L1 and L3, M3 and M1. What can L1 and L3 be for this equation to be equal to 0? How about if I have L1 equal to M1 and I have L3 equal M3? Yep. Then that's 0. You agree? And then here I have L2 equals M2. So I'm going to have L2 equals M2 and L3 still is defined already here as M3, and that will also equal to 0. So I'm going to end up with this. Excellent. Right? This is what I want, isn't it? Right? This is perfect. So this leads us to the correct solution, except for the fact that there is another solution. Anyone can tell me what that other solution is? Found it? Not all zeros. Is that what you said, all zeros? Not all zeros, no. Consider the case where all PI's are on the same plane. Pi. Okay? Remember when we defined the equation of a plane in homogeneous coordinates? So now you can set L1 equals to pi, right? In homogeneous coordinates, equation of a plane in homogeneous coordinate. L2 zeros and L3 a vector of zeros. Okay? Then what am I going to have? I'm going to have pi, let's see, what did I say? L1. Okay, so L1 is pi here, right? So what is pi times pi? Remember, pi, it's a point on that plane. So pi times pi, it's equal to 0. Good. And this L3, we set out to 0. So this is 0, 2. So this equals 0, right? So that's a non-trivial solution because here are not all the vectors equal to 0, but yet that gives me 0. And then the same is going to happen here, right? I can set out any value here that is going to give me pi times pi equals 0, or 0, 0, as I have set out here, is equal to 0. So either this or that. Or the other one, where pi is equal to L3, they're all possible solutions, right? What does this mean? It means that if I give you a picture of this, and you take all the PI's from that plane, you're going to get the degenerate solution. That's exactly what it means. And depending on which of these three planes you select your points from, you're going to get one of these three possible degenerate solutions. See how this works? So when you do calibration, you have to have points ideally from all the three planes that you're given, right? Don't go with your G input and say, okay, this one, this one, this one, this one, this one, this one, and I'm done. That's not going to give you a solution. Well, it's going to give you a solution, but it's not the solution that you want. That's a solution that you want, right? So remember that there are other unwanted solutions. All right. Any questions? All right, so before we continue with this, I mean, this is all about camera calibration, but before we continue with geometry, I want to briefly talk about the human eye and some similarities between what we're doing between cameras and the human eye, some dissimilarities, and importantly, some applications of what we're doing to study the human eye as well. Okay? So let's see that. Now, the reason I want to do this is because if you open any book that talks, I mean, not any book, but especially generic books for the general public, right, about cameras, the very first thing they're going to show in page 1, maybe page 2, is the drawing or a picture of a camera and a human eye, and say, you know, they're the same thing. No, they're not. It's not even close. So let's see what the human eye is, or how does it look like. So I'm going to try to do the drawings here. You have the slides online in Carmen, which have really nice drawings, so use those, right? I mean, I say this because I always see people taking pictures of the whiteboard, which is great. I don't mind. But you know that you have all these equations and all the drawings well done in the slides, right, in Carmen. So let's see if I can draw an eye. And what I'm going to do, I'm going to draw a section, obviously. I'm going to attempt to draw a section, rather. Oh, boy. OK. All right. All right, so this is a section. Excuse me. If you saw my face sagittally, this is a sagittal view called, or side view, right? And my eye is looking forward, and now we slice the eye like this, right, in half. And I show you the sagittal view, right? So that side view of that cut, that's what you would see right here. And you would see this thing here, which is the cornea of the eye. This is what you see at the outer part. You see, if I touch it, right? If I touch my eye, I'm actually touching the cornea, okay? These two things here that I've tried to draw, these are muscles. And these muscles move to form the lens that you have behind the cornea. Now, this is extraordinary. Cameras have lenses, right? This is a lens, right? Right here, you can see the lens of that camera, right? So cameras have lenses. In good cameras, right, an SLR, for example, you can buy lenses that you can take out, put in, and really large ones that can focus really far. They can get you really well-focused and very large zooms of images or of objects that are really close or really far, right? Fantastic lenses. But they're rigid lenses, right? The way that we change the focus and the zoom in and zoom out is by moving the lens, right? Or the focal length from the lens to the image plane, right? That's how we create that change of focus and zoom in, zoom out, as we showed here in the equations. That's not how the human eye does it. Human eye doesn't have a lens that moves forward and backwards, right? The focal length doesn't change. The lens stays put. But you have two muscles that can deform that lens. This is insane. Can you imagine if we could design deformable lenses? And there are people working on this, obviously, right? Can I design a deformable lens that I can put in a cell phone or a very tiny camera like this that is able to focus or zoom in, zoom out on objects by deforming the lens rather than moving the lens, right? Rather than changing the focal length. That would be ideal if we could do that. But how do you come up with materials that have the properties of a lens and are deformable? That's the question. So that's what people are trying to solve. So that's a huge first difference between the human eye and cameras. The lenses that we have are completely different. What else? Now, if I have an object here, a three-dimensional object, and I have a point P and Q, then what's going to happen is the light, right? So I have a light source as always, right? This is my light that emits some energy, some photons toward that point, and then they get scattered in multiple directions, and in one of these directions hits the cornea of my eye. Now the cornea is going to bend that light, then that's going to hit the lens, which is going to bend that again, and it's going to give me this point here, and the same is going to be happening here. It's going to bend again, and then I'm going to get my image points right here at the back. Okay? Same thing. Now this back side of the eye, where I have my vision, right? All this is called the retina. That's where I imprint my image, right? That's my image plane. And it's curved, big deal. It just happens to be curved. But there's something funny about that image plane, isn't there? This is something really weird. What is it? Anyone can point me to that? I draw a hole right here. Do you see that? What this is, and we'll get to this, there are a certain number of neurons here, right? There's an epithelium, we'll talk about that, that imprints the image, and then there are a certain number of neurons that read that information from the epithelium and then have to send that information to the brain. So our eyes are right here, right? And then these neurons at the back of the eye, in the retina, they read the photons that we receive. Some cells are called cones and rods that we'll define, that read that information, pass it through some pre-processing through some neurons, and then have to send that information to the back of your brain right here, and it gets called the occipital lobe, where it gets processed. It first has to pass through another area of the brain that's called the LGN, but details, they're not important right now. But the signal has to be sent to the back of the brain. Well, these cables, right, the axons of the cells, of the neurons, have to go through someplace, and they just happen to go through here. So you collect all the axons, all the cables, so to speak, of every neuron will travel through here, and this other one will travel through here, and this other one will travel through here. So this is all the axons that send the information to the back of the brain. Okay? But what happens because of this, you have no vision here. Now, I'm sorry to disappoint you, but there is an area in your visual field that you don't see. Now, that sounds really weird, and I know you don't believe me, and that's why I brought proof. So you probably have to share this every 2 people, because I only have so many. Can you pass these back? Pass back. Share it every 2 or 3 people, share it. So here's the way this works. There are 2 examples here, okay? Let's do the first one, the top one first. If you close one of your eyes and you look at the first row, pointing at the cross right here, or at the other one, it doesn't matter, one at a time, right? And you put this at a specific distance where that object falls into your blind spot right there, then that object disappears. And if you look at this cross right here, you have to close one eye, just with one eye. And then if you look at this cross right here and you move this back and forth until this line becomes continuous. And that's because this empty space actually fits the blind spot, and the brain is constantly inputting information, lying to you, telling you that I can see what's in here, but because it cannot see it and it sees this continuous line, it assumes that there is a continuous line. So it actually makes it solid. So again, fixate on the cross, close the right eye, and hold the figure about 1.5 feet from your face. Right there, my circle just disappeared, and the line is filled. It's amazing. All right, have fun. I'll see you Thursday.